Hello, everybody. My name is James Powell, and welcome to the DOE Python Exchange. We are joined by a new group of host panelists who will be leading us through a fascinating discussion related to everything that comes up when you're doing scientific computing using open source scientific computing tools like Python. As with all of our calls, we'll start off by first giving each of the host panelists an opportunity to introduce themselves. Then we'll do a little fun activity joined with our host panelists, and then we'll jump into some prepared remarks that they have for us, but finally ending with some open Q&A and discussion, where we hope that you'll have an opportunity to reflect on some of the prepared remarks that the host panelists have provided to us, as well as an open opportunity to ask any questions that would help you do your research better. And so with that said, why don't we start off with our introductions of all of our host panelists today. As is our convention, we'll start off by first introducing ourselves, letting everybody know what kinds of questions we would love to help answer, and any other details that'll help form the best possible discussion that we can. So I'll get started. My name is James Powell. I serve to provide training for folks working within the national labs. If you're interested in asking about how do I make sure my scientists are actually writing good code, that's something that I'd be more than happy to opine upon. And I'll hand it over to Cameron next.
Hi, everyone. My name is Cameron Riddell, and while I'm not specifically affiliated with a lab here, I do have a background in academic research where I studied cognitive sciences. Specifically, I was working on modeling visual working memory in humans, as well as the interactions between stress and long-term memory. I work with James, helping provide training here as part of the National Lab System. And for today's discussion, I would love to field any and all of your questions related to just Python in general, or specific concepts and uses within its vast scientific computing ecosystem. So things like tools such as NumPy and Pandas.
Cameron, why don't you hand it over to our colleagues from BNL?
Yes, so looking at our first BNL colleague, Dan Allen, I would love to hear about you, what your affiliation is, and what you want to get from this discussion.
Sure. I'm at the National Synchrotron Light Source 2 at BNL. I'm trained as a physicist, but I've been doing open source scientific software and not so much herding cats as learning how to be herded by cats, collecting requirements from the 29 different scientific instruments we have here, and increasingly our collaborators across the DOE and the world. So happy to take questions about building projects collaboratively and navigating the tension between the overlap and the different things that people need to do with scientific software. Maybe I'll hand off to Andy.
Thanks, Dan. I work at the same institution that Dan does. I'm maybe one of the cats he's speaking about. I'm a beamline scientist with training in chemical physics. I spend a lot of time sort of in between expert developers like Dan and people that have never used Python before to do experiments and analyze data at NSLS2 exclusively in Python. These are the kinds of things that I can help answer to sort of make code more approachable, and also just generally enthusiastic about using open source for scientific understanding.
Andy, why don't you hand it over to Matthew?
Yeah, Matthew, as a colleague at BNL, but go ahead.
Me, right? No, I'm not sure if the other Matt is on. Yeah. Hi, everyone. I'm Matt Carbone. I'm an assistant computational scientist in the Computational Science Initiative at Brookhaven National Lab. I am also a physicist by training. I did my Ph.D. in theoretical condensed matter. But of course, now I do mostly computational science, which includes some of that. I would say my subject area, feel free to ask me whatever. I can take, Python questions. I can take HPC questions. I specialize a lot in applied machine learning techniques for the domain sciences. But in general, anything related to numerical scientific computing, including machine learning, I'm very comfortable with. So thanks, everyone.
Don't tell them you know machine learning. Everybody's going to have a question for you, Matthew.
Yeah, I know how it goes. I'm used to it. It's totally fine.
And why don't you hand it over to Tanny?
Hello, everybody. My name is Tanny Chavez, and I am a postdoc at Lawrence Berkeley National Laboratory, so a different laboratory. And my expertise is mainly in machine learning too. Basically how to make or deploy machine learning algorithms and make them accessible to a larger audience, in particular in this case for beamline science. So I'll be happy to take any questions related to that. And that will be me.
And Tanya, if you could hand it over to our guest panelists for this week, starting with Gordon.
Sure, go ahead.
Thanks. I'm Gordon. I'm from the University of Washington, and I'm part of this initiative, which all three of us are part of, this IRIS-HEP, whose goal is to improve the software environment for the high luminosity LHC, a project that's coming. Well, it's been delayed a little bit by COVID. And I specialize in analysis and understanding and looking at the tools in the Python ecosystem that can be used to build a better and more efficient analysis. As far as the type of questions I get, if somebody has a Fortran question, I'm there for you. I'm there for you. But more seriously, this is just because I'm old. Having been trained as a physicist, of course, I've been through many different tool sets. And I'm particularly, because I still work in the science, I have a pretty good overview of the interface between the programming and the science. So any questions along those lines or Python, etc., I'm quite comfortable with. But not as comfortable as my two colleagues who are true experts. So first I'll introduce Jim Pivarski. Jim?
Okay. Hi, I'm Jim Pivarski. Research scientist at Princeton. I was trained as a particle physicist, did particle physics until about 10 years ago, then went into data science, before it was called that, as a consultant, and then came back to this field. Now basically developing tools and like data science like techniques in the high energy physics community. So I'm developing tools, so software developing, and helping people use it, answering lots of how-to questions and such. So I'm comfortable with that sort of thing too. So next is Matthew.
Yeah, hi, I'm Matthew Feickert. I'm a postdoc at the University of Wisconsin-Madison, where I'm jointly at the physics department as well as the data science institute there. And as Gordon and Jim mentioned, I'm colleagues with them on IRIS-HEP and then also on Peickert-HEP, which you'll hear about today. And a lot of my kind of, I guess, focus or work right now is, as you can kind of imagine, is on data science workflows with the analysis tools that we're building in IRIS-HEP for the broader particle physics community, as well as doing statistical inference. And something that I'm interested in, I don't know if I'm really an expert, but I'm happy to discuss with, is how to try and build community around tools and around projects where you not only have people coming in as users, but hopefully sticking around to contribute ideas as well as code.
Fantastic. So if you are new to this call, do know that we have both a Q&A widget and a chat widget. And so if anywhere along the way you'd like to ask a question, feel free to use either that chat widget or that Q&A widget. While our guest panelists are providing their prepared remarks, the remaining host panelists will be monitoring both of those to answer any questions for you live. So don't worry about interrupting anybody. We're more than happy to answer questions while the guest panelists are providing their prepared remarks. But first, we have a little activity for you. And so in order to prepare that activity, why don't I share my screen? Behind me, you'll see my screen, and I will hide in the corner here. And our activity, our coding activity for this month's Python Exchange is a little game called Worse Than Nothing. Because some people say that something is really better than nothing. And I want to figure out with our host panelists, is it really true that something is better than nothing? Here's how the game works. There are 3 rounds plus a bonus round where I'll present you with something that we tell scientists are just universally good ideas. You should always do this. And I'd like if our guest and host panelists could share with us situations where, you know what, don't do that. if you didn't do it, it would be better than if you did it at all. Our host panels and our guest panels will be scored, not really, on the specificness of their responses, with some bonus points for situations that can point to where some researching scientist has done something, and you're like, you know what, just don't do that. Honestly, that's worse than nothing. And so to start us off in round one, comments in your code. When is it the case that a scientist adding comments to their code could be worse than not even bothering? It's worse than nothing.
Can we just jump in?
Go ahead, yeah.
Okay, because this one I feel kind of strongly about. It can often be the case that adding comments is worse. Because comments are stating something about the code that is not checked by any kind of compiler or any kind of runtime test, and easily gets stale. So when you're adding comments, you've got to be careful that you're adding something that is at a general enough and a high enough level that it will always be true, unless there's some major rewrite of the software. If the comment is something like, this adds 5, for one thing, it doesn't really add anything, because if you can read code, you can read the English. If they say exactly the same thing at the same level of abstraction. But worse than that, when it's changed so that it adds 6, the comment will be misleading, and it will send someone in the wrong direction, and they'll waste a lot of time on it. That's my 2 cents.
Oh, yeah, I'm going to come down a little different from that. Having worked with grad students, and having observed 10,000 line functions which have 0 comments in them, maybe it's okay not to have comments if you've followed all the good software practices of making small, 10 to 15 line maximum functions, separating things out into files and modules. But many people don't do that. And, despite my threat of you can't graduate unless, sometimes it's not convincing enough to get them to follow those practices. And in those cases, high-level comments, as Jim said, are very convenient. And I often find for functions, even well-written ones that are short, especially ones that have a public API, the header comments that describe what's the point of the function, absolutely crucial. I know some people who document their functions just by test cases, and I can't read the test cases, often because the test harness is already so complicated, I can't see through it. So I'm big in favor of comments at that level. But yeah, +5, I agree. Better just never to do that.
Yeah, I think. Oh, sorry, go ahead.
First Cameron, then Matthew C, then Matthew F.
Okay. I was going to agree there with Gordon. I actually was just working on a problem in Pandas, and shame on me, I was using their _led private attributes. But there's a private attribute called is_copy. Just by the name of that, I would expect it to be a Boolean, true or false. This is a copy of a larger data frame. Turns out it returns a weak reference, right? That returns the parent's data frame that you extracted it from if it's a subset. So if I didn't have those nice comments there to help disambiguate this misleading attribute name, I would have been lost for a little bit.
Matthew C?
I can go next. Matthew F was talking first if he wants to go.
We'll do Matthew C, then Matthew F, and then we'll wrap up the round.
All right. So good comments are good, bad comments are bad. That's my sort of, just Cameron, to address what you were saying, that even though it's a private attribute, right, because Python doesn't have private attributes, right, even though it's a private attribute, right, it was very badly named. So the comment shouldn't even be necessary. The attribute should be better named than it was, right? But certainly I agree with what the group has said. A comment that doesn't change as the code changes, or a comment that is so, just restating something obvious that your code is doing, right? That's not the point of the comments. The comments are to be an aid to better understand what the code is doing, right? And if it's not doing that, then there shouldn't be a need for the comments. And if your comments are trying to explain a variable name, the variable name should be changed so the variable name is clearer. You shouldn't need a comment to say, really what a variable name is. The variable name should be self-evident. In fact, I don't remember where that's from. There's some standard that says variable name should be self-evident or something like that. I don't remember where. Someone can maybe tell me what that is. But yeah, that's my comment.
Fantastic. And Matthew F. with the last comments for this round.
Yeah, I think everyone's already made really great comments, and I think I generally agree with all of it. But yeah, I think, maybe asking the question, who is this code for and who is going to be reading it in overtime, and what's the life cycle of it? These are all important questions as well, because if I'm a developer and I'm thinking, maybe I should add some comments here, then as was already brought up, why am I adding a comment? Is this something that I should be refactoring, or is this something that I should be trying to clarify in the code? Or, doc strings are such an important tool, and we live in this kind of golden age of documentation systems right now. So it feels like if you can share that, then go for it. And I guess maybe also coming back to the, the is 5 or is 6, if something is just going to get a throwaway comment, then again, maybe it's a time to think about a good hard refactoring. Or, if it's actually deserving of a comment, be verbose. We don't really need to, care so much about if Python is going and ripping out those comments for you later on. But 2 a.m. or 3 a.m. you probably will thank you for it.
Fantastic. Why don't we move on to round 2? And for those of you just joining us, we are playing a game. When is worse, better than nothing? In round 2, documentation. We tell scientists all the time, write documentation for your code. When is it the case that writing documentation for their code is worse than just not even bothering in the first place? And I'd love to hear from some of our panelists who are quieter in round 1, Tanny, Andy, and Dan Allen, if they have any thoughts for when is documentation? Just don't even bother, better not.
I think I probably have an idea here. Something that comes to mind would be, what if we don't update the documentation? Like, we have made updates to the code, we have added all these cool techniques, all these cool approaches, and the documentation is still the same one as it was in version 0. I'm guilty of that. So speaking here about experience, something, think about how to keep up. In this case, it's documentation. I think that's probably something that comes to mind, that it doesn't make sense to have several pages of documentation if that is entirely outdated. So that comes to mind.
I'm curious to hear from Dan. Dan, does anybody actually read documentation, or do they just skim to the bottom, find the examples, and cut and paste them into their code?
I hope so. I spend like half of my life lovingly writing documentation that probably only I read. But a thing that I have started sneakily doing to avoid this kind of worse than nothing problem is I do like to do documentation-driven development. I like to write the explanation of how to use it as I'm designing the API, because if it's hard to explain, then no one will use it. But I don't always publish that documentation yet, because if I'm not sure I want to maintain this for the rest of my time at NSLS2, I might write the documentation in secret, put the tool out, tell a couple people about the secret documentation, let them use it, while I can still change it. And that we find is once you teach people to use something, you can never fix all the problems. They'll immediately find with it. And trying to delay that moment where it would be painful to fix things in response to feedback is a reason why nothing can be better than documentation.
And I'm also curious to hear from Andy. Andy, you ever looked at some code and it was so thoroughly documented with hundreds of pages of stuff that you just rolled your eyes and you're like, oh, come on, I have other things to do? How could they have done that better? Oh.
I don't think anybody ever complains about well-documented code. I think the problem comes when it's not updated or relevant or difficult to find the newest version of the documentation. So I think if you don't have the tools to keep the latest version of the documentation easy to find, this would be a challenge. I think maybe adding like links to your documentation in the doc strings can help with that. I think personally, I don't write a lot of documentation because my code is changing a lot. So I put stuff in doc strings because at least that can be, in a very slapdash way, made into some kind of documentation.
And I'm surprised nobody commented on What happens when the documentation doesn't match up to the comments or doesn't match up to something else? What about documentation that tells you a different message than something else, documentation that is otherwise conflicting or confusing? Cameron, did you have one final comment to add on that?
Oh, no, I didn't. I was just eager about the next point. But there just have been some projects, right, where you're reading through maybe a tutorial or something, and you're like, oh, man, this is exactly what I'm looking for. Copy and paste the code example, and it doesn't work on whatever current version you have. It has to be the most frustrating thing I have ever dealt with.
Okay, fantastic. So let us move on to our third round. This one's an easy one. Testing. We tell people, write tests. You should be writing tests for your code. Why doesn't your code have tests? When is it the case that writing tests code is worse than nothing?
Yeah.
I can say something if you
Go ahead,
like.
Gordon.
I don't know how you're doing the ordering here.
Go ahead, Gordon. We'll start with you.
Okay. Yeah. So this actually intersects with the last point. There are now systems where you can put tests in your doc strings and then run them as part of your build. My favorite sets of tests are when I arrive at a repo, sometimes it's my own, and I run all the tests and they're all green and it's great. And I go to modify something and then go look to see if any tests have failed. No tests failed. So I know I broke something. So I start looking at my tests or whoever's tests a little more carefully. And I realize about 80% of the tests have a skip or other mark on them because they were just too hard to maintain. And this is one of those cases where you get this false sense of security. It's tested. I made the modification. It's going to work. I'll ship it and not look too much further, too closely at it. So I think those are cases where it's just not worth writing the test. If you're only going to cover 15%, it's worth it because eventually it will build, but it's not worth it to trust it as if it were a fully tested package.
Does anybody want to comment on the other situation where the tests fail and then the author says, no, don't worry about those ones. Those ones always fail. That's not the one that you have to pay attention to.
No, we would. Okay, can I go?
Go ahead, Jim.
Yeah, no, like that wouldn't even pass continuous integration, which is the thing we should have. I actually with tests, yes, absolutely. There's some things you want to test and other things you want to not test. And I think this is important to think of. Have you ever done like biology and you're like dissecting a frog or something like that, and you put pins in, and that's going to hold some bits while you're getting out of the stuff. You don't pin everything. You don't turn the frog into rivets everywhere. You just put them where they need to go in order to hold the structure together. And that's how I think of tests when I'm building tests. So like when the test does some computation and there's a result, you absolutely don't want to test the string representation of the result because you want to be able to change that. You want that to be able to change by a character or two characters or whatever. That must remain flexible. That must be allowed to flow. But the thing that you want to fix is like the numerical results with some precision. So I test out a prox, that kind of thing.
Building on that comment.
Dan, for the last comments.
Yeah, sure. Greg Wilson of Software Carpentry had a great series on how testing scientific code, it leads you toward trying to test trends rather than exact equality. As Jim said, you can test an exact result within some approximation, but if you're working with real data or some realistic situations, you might improve the code and change the result as much as make the code worse and change the result. And so trying to test that things tend to converge a certain way or that something should be greater or less than something else is a really tricky aspect to scientific computing in particular, finding the right way to express that.
Fantastic. And for our final lightning bonus round, code. When is it the case that writing any code at all is worse than just not even bothering? Just don't write any code for this. Keep it in a notebook. do whatever. Don't give me a library.
Wait, so what's the distinction? Writing like a software package, you mean, versus a Jupyter notebook, or are we talking about writing code versus just not writing?
Tell us. When is the case where you say, don't bother, don't write any code?
I can speak to this. I mean, because it's the over-engineering problem, right? Like, if you're going to take 20 hours to write a software package that only you're going to use, and it's going to solve a problem that should have taken 5 minutes, probably not worth it. The reason I can speak to this is because I've done this many times, where I've been like, oh yeah, people are going to use this. I'm going to use this all the time, right? Spend hours and hours and hours trying to create the perfect package, and I just forget I have a research question to answer, you know? So my guilty comment on this is my first paper is entirely done in Google Colab Notebook. Why? Because I could, you know, why? If it works, right? For that purpose. But, you know, I think it gets a little tricky, right? Because if you're writing it in Colab notebooks, it's very, very hard to actually test it. And then you fall into the, you know, what Dan basically said, which is, you know, my interpretation of testing trends, not exact results, is the compare to the literature test, right? So you have a code, and if it reproduces literature precedent, you give it the stamp of approval, and you're, especially in physics, I do this all the time, right? And you're good to go. So, but I think at the base level, if you're over engineering and you don't have to, that's a time where you shouldn't write a big software package. Go and look and see what's out there. Use a Jupyter notebook, get your research done.
Yeah. I would like to
want to speak to the once you write it, it'll live forever problem. Andy?
Yeah, I mean, I was just going to say, I think it's, you know, Matt just sort of reminded me of something. It's worth the internet search time to see if somebody else has started something that you might be able to use, because why reinvent the wheel? I mean, and then maybe you might even form like a really nice collaboration to work on something. There, you know, I can't even count on one hand all the packages that exist to do reflectivity, right? They're all needed, but I'm not going to write my own.
Any final comments? Dan, Tanny, final comments?
I endorse what Andy said.
Dan, I had one question for you. What about maintaining something? Is it worth writing it?
So I guess my comment would have been the worst code that gets written is the code that only one person understands, several people rely on, and then they go and work in industry. That's the code that shouldn't get written.
So it would be better if they didn't even bother to write it in the first place. Then you'd know you're on your own rather than relying on something which may not be that reliable. Well, yeah. Thank you to all of our guest and host panelists for playing the game successfully, tallying up the scores. It seems like we are all simultaneously winners and losers. And with that said, why don't we move on to our main attraction for our Python Exchange call, some prepared remarks put together by our guest panelists, Jim, Matthew, and Gordon. Let's jump right into it. Gordon, Jim, and Matthew, how do we want to get started?
Great. So I'm going to go ahead and be driving because we're doing a joint presentation. So we'll just be doing some verbal handoffs. So I'm going to go ahead and get sharing. So hopefully everyone can hear and see me okay. And if so, then let's go ahead and get started. So hi, everyone. Thanks so much for tuning in today. Also, thanks to some of our colleagues who are in chat as well. And today we're going to try and give you hopefully a short overview on just the kind of modern Python analysis ecosystems that are for high energy physics and how we're personally kind of involved with those efforts. So to begin with, on slide 2, hello. So we're all members of the Institute for Research and Innovation in Software for High Energy Physics, IRIS-HEP, as well as also the Scikit-HEP community project, focusing on developing a Pythonic data analysis ecosystem for high energy physics. So IRIS-HEP does a lot of things. So it's involved in data delivery and management. It's involved in cyber infrastructure. It's involved in, actually providing support for continued development of existing scientific software that already exists. And then it also has been an intellectual hub for software development in general, and also a kind of nucleating site for the Peickert project in general. But both of these projects, we share kind of a common goal across them in that we want to try and empower analysts at the Large Hadron Collider and beyond with modern data science tools, as well as provide them with powerful libraries for building expressive analysis workflows. And then, sorry, before I go on, just to make sure that I don't have things not working properly, do people see a black square at the bottom of my screen, or is that properly hidden?
You see it.
Okay, let me see if I can put that away. Okay, that should be gone now, hopefully.
Yeah.
All right, sorry about that. Okay, so moving on to slide 3. So given that we're at a Python exchange, we're not going to do a why Python slide because I don't think that anyone here needs convincing, but we're gonna take just a brief aside to try and give a short summary of the essentially the story of how our field went from being a predominantly C++ dominated field to kind of a 2-language field of both Python and C++. So here we're looking at a plot that I'm going to try and walk you through, which is actually a study that Jim Pivarski did, where he looked at the members who, he looked at the people who had forked a GitHub repository called CMSSW. And what CMSSW is the open source software framework for the analysis software framework for the CMS experiment. CMS is one of the 4 main particle physics experiments at CERN's Large Hadron Collider. And so you have thousands of physicists who are all working and contributing to this. And the reason he did this is because CMSSW is a necessary requirement to actually do analysis work on CMS. And so if you look at people who forked CMSSW, you're essentially filtering for people who are particle physicists on the CMS experiment. So what he then did is he went, and now that he has this list of people on GitHub who are CMS experiment members, he was able to look at their repositories and then search through them, or the open source ones on GitHub, and look at the import statements that exist across, and then filter those across languages. So we can see as we move through time, left to right, that things start off as a very C++ dominated world where there is still Python, but that's kind of mainly configuration languages. And then around late 2017, 2018, we see that things are changing, that now Jupyter notebooks are being used in analysis. And then additionally, that we actually see that Python scripts, presumably for analysis, are getting used a lot more as well. So we see that there's definitely this transition to Python being a very dominant language. On slide 4, if we zoom in a little bit and become basically on the same data, we see that this coincides with a rise of scientific Python in high-energy physics experiment code, where we see things like NumPy, Matplotlib, Pandas, and TensorFlow. So a lot of the things that people who are doing data science-y like analysis and scientific computing would be using, we see kind of an explosion of this compared to some of the C++ tools that you can also see here, like Root from 2018 on. And then as kind of a spoiler, you can also see that we have these packages that are called Uproot and Awkward that come from Scikit-hep that we see from 2018 on are also starting to make an appearance. And so this rise is not really super accidental. This is also very tightly coupled with the rise of Scikit-hep and with the IRIS-hep ecosystems as well. This plot here on slide 5 is showing the number of pip installs of Scikit-hep, IRIS-hep, and affiliated packages per month. And we see that between 2018 and 2020, we basically have a 50x increase. And this is also being filtered on looking at installs on macOS or Windows in a bid to try and make sure that we're not catching batch jobs on high throughput computing systems or Linux CI. Obviously, you are still going to get CI jobs for macOS and Windows, but it's certainly going to be less than the Linux jobs that are being filtered out. And if we also see that these are popping up in macOS and Windows jobs, then this is also probably a sign of growth as well. And if we again get a little bit more granular, what we see here is that it's not just that there's more people using existing tools, but that there's more tools as well. from 2018 and 2019 on, we see that each of these lines represents a scikit-HIP, IRIS-HEP, or affiliated package, and we see that not only is there growth in them in the number of pip installs, but there's also just more lines in general. So as the ecosystem grows, so does the community adoption. So on slide 7, speaking of ecosystems, this is probably an image that many of you have seen many, many times. This is, of course, the kind of iconic PyData ecosystem shell or hierarchy view that was first introduced by Jake Vanderplas in 2017, where at the bottom or the inner runs, you kind of have the most broad and software and technologies. And then as you move further and further out, you start to have more focused or bespoke libraries and tools to try and solve different domain-specific problems. And so on slide 8, we have basically, this is what maybe a 2022 view of the Pi-HEP ecosystem would look like for scikit-HEP and IRIS-HEP and affiliated packages as well, where again, we kind of have the same hierarchy. And in slide 9, just to kind of run you through just some, to give you some exposure to what we mean when we say this, because probably you're not as familiar with all of these. In the lowest or most inner shell, we have the non-HEP software that we depend on. So basically, the first 3 or so tiers of that PyData ecosystem, all things that are truly foundational for our analysis. And on the second run, we have things that really aren't specific to particle physics per se, but such as like histogramming and jagged data structures. Like these are not, owned by high-energy physics, but they didn't really exist in the broader ecosystem in a way that we could use. So we had to create our own libraries. Tier 3 is where we actually start to see some of these like truly like HEP foundational libraries for reading and writing domain-specific files, as well as working with things like 4 vectors. And then we move further out to try and focus on things that are libraries that are solving common problems in particle physics, but probably pretty specific to particle physics, such as performing bins, maximum likelihood estimates, and in very high dimensional space using uncertainties that are physics aware, performing typical cross checks for analyses, and then also trying to make publication ready plots and visualizations that also conform to experiment specific guidelines. And then the very outer run is basically focusing on truly HEP-specific sorts of algorithms or applications, such as integrating with physics simulators or things like that. But something that I want to try and focus on here, and as Jim, who I'll be handing off to next, will kind of tell us a story about in the form of a few use cases or studies, is that this whole ecosystem is built with a focus on interoperability. So with that, I'll hand this off to Jim on slide 10.
Okay. So switch on video, that worked. All right, so here on slide 10. So I'm going to tell a story about histograms, because in particle physics we use histograms a lot, and we use them in a special way. I'm not getting into too much detail about it, but we need the histograms to be objects that we can store and pass around rather than a display style for a plot. So when physicists entered, so let's go to the next slide. When physicists entered this area, we saw that there was a lack of our type of histograms, and so we want to make this kind of library. And you think about it, in Python, it's easy to write this kind of thing, especially for histograms. You make a class, an object, just bin and count within that. It seems easy. So next slide. Well, in fact, it's so easy that physicists have created at least 20 libraries in Python, and most of these. So actually, I followed up on all of these. These are all physicist histogram libraries. So, this clearly too many, but none of these actually really took off. I'm sorry, most of these didn't really take off. Some of them really did. Okay, page 11. And in fact, here I went and followed up on each one of them and looked at the number of committers to these libraries, because they're all Git repositories. Number of committers to these libraries versus time, and here we're looking at the number of unique monthly committers and it's smoothed. So what we're seeing here is there's some projects like Roots where that goes back to 1995, and the maintenance has been stable. It's just a very well maintained project. It's primarily C++ project, but they have a Python interface. There are other long-term things like Yoda used in the theory community. There was a RootPy project that really flourished right before our field moved in a large way to Python. If you remember from the earlier plots, it was really after 2015 that the turn-on of starting to use NumPy and Matplotlib really happened. So RootPy came too early. Then when we moved to Python, this is the area around 2017, you can see there's a lot of libraries in there, and most of them don't have a lot of unique committers. This is when many libraries were born and died. This is kind of not what you want to have happen in an ecosystem. But then since then, there's a group that I'll be getting into more detail in the next slide of Boost Histogram, HIST, and MPLHEP, which work together to provide histogramming in high-energy physics. And for that group, the number of monthly committers is really quite high. This is a very actively developed project. And you can see there's another one here, histograms in Coffee. Coffee is another major project, and they are switching to use Boost Histogram, HIST, MPLHEP histograms. So let me explain that group in a moment. Next slide. So what this is, these are separate packages. Each one of these boxes is a different pip installable Python library. Sorry, the first one's C++, Boost : histogram C++. That's wrapped with Boost -histogram. And that's a thin wrapper. And then there's a fully featured, very analysis-ready HIST package where you can just say pip install HIST and you get histograms. Then there were other projects that were developing plotting of histograms in Matplotlib, but without having a histogram object, histoprint, MPLHEP. And then all of these, they are all accessible from HIST. So originally, each of these packages were developed by a single author, like the many things. But then we talk to each other. We recognize, okay, it's valuable for this package to focus on, Boost Histogram focuses on fast filling, using C++. HIST focuses on the total user experience. MPLHEP focuses on plotting in Matplotlib. Histoprint is for printing out a histogram on the terminal. So they each focus on a different thing, and these packages know about each other. The authors collaborate so that we're doing this sort of distributed development of a feature, an ability. So actually, there's now 47 developers contributing to these packages, and 20 have contributed to more than one. So this is really what we want. It's like a mesh of development. Next page. The way that this works, the way that these different packages can nevertheless agree is because we define protocols of how they talk to each other. And there's lots of arguing about what exactly should go in the protocol, and that's good. Then we get something that we're all okay with, and then they can talk to each other. That's how it works. And so I consider this histogram story to be a big success story. Next page is a totally different thing, but I wanted to talk about a few case studies. So another need that we had were arrays of non-tabular data. Almost all HEP data consists of these variable length lists and nested objects. This is why traditionally we've been using C++, because you can do standard vector of class instance, right? So if you were to try to describe them, you wouldn't be able to describe them as a table very easily. The best description you could make is JSON, but JSON is wildly inefficient for the scale of the data we need to do. And also, if we want to interface with these NumPy-centric tools, what we need is something array-like. So we needed a way of accessing such data in a NumPy-like way. So we got this thing. This example, it looks like JSON is representing data that's, these would kind of be like class instances of some kind of class that has X and Y fields. and they can have all different types. They can be in variable length lists, and they can have variable length lists. And what you want to do, next slide, is you want to do NumPy-like expressions. So you want to be able to slice them, apply some NumPy ufunc like NumPy square to the whole thing, and then just squares all the numbers. So this is an example of doing some NumPy-like operation. Next slide. This is what you would have to write in Python to do this. In fact, this is what you have to write in C++ to do this, except they're C++ for loops. So we make things a lot more concise, and you get to work from Python instead of having everything be in a compile cycle. And also, the thing on the left is 100 times faster than the thing on the right. So, and now my last slide before handing it off to Gordon is showing that in the few years that we've been doing this, developing these tools, it's now getting to the point where whole analyses can be done in Python using Pythonic tools. And so this is an example of one. And they're starting to they've gone through the pipeline, and they're coming out the other side into published papers. So, Gordon?
All right. Sorry. Okay, thanks, everyone. I'm going to take a slightly different track and talk about something higher level now. So Matthew and Jim have really concentrated on the ecosystem. I'm going to talk a little bit about taking advantage of that and the open source ecosystem in which all of the scientific computing exists. I want to talk a little bit about the initial phase of doing data analysis. So this is where we have to start from a very large data store, maybe petabytes worth of data, something that we have got to be able to scan over in the high luminosity LHC project. Of course, petabytes of data are too much to handle and reason about in any real way. And a standard physics analysis will only need to grab a small part of it. So this is a story about how we might extract that small piece of data to then reason about, make histograms, and analyze with some of the tools that Jim, for example, just talked about, and more generally some of in the ecosystem that Matthew just talked about. Can we go to the next slide, please? Okay, so in the standard sequence for data delivery, we might start with our detector. We take the data, the raw data from the detector, we reconstruct it. It is then stored in some huge centrally organized, for lack of a better word, data lake, which I realize is both meaningful and meaningless at the same time. These large data sets now, which are petabytes in size, we then scan to extract exactly the data that we are going to need in order to do our physics analysis, to make the plots, to construct the statistical models, to train our machine learning models, etc., and then hopefully publish a paper with maybe even a discovery. The standard way we do this in particle physics is we take these large centrally managed data sets, skim over them with something written in C++, and create a private skim. These private skims can be hundreds of gigabytes in size. They contain everything that you might ever want because it's very expensive to make them. So you try to think ahead. You don't just go after the things you know you're going to need. You go after everything because remaking them is so expensive, and you can't go all the way back to make your physics plots. You have to start from this prefetched data. This requires large intermediate files, and if you look through what's going to happen in the high luminosity LHC, disk space turns out to be one of the biggest drivers of cost and problems it will constrain the physics that we have to do if we do not manage it carefully. And further, a lot of experiments have been moving towards common formats, but these are becoming less and less adequate now as deep learning becomes more and more prevalent in our analyses. And I'm talking about deep learning that's using low-level features, for example, hits in the detector. There's a lot of disk space involved in extracting those and saving those hits. And so as a result, the common, highly compressed common formats tend not to have this low-level data, which makes these sorts of deep learning algorithms difficult. As I mentioned, runs over the centrally managed data sets to produce a private skims can take days to weeks. This is wasted analyzer time, of course, and it also means if you've got an idea, you effectively just have to chalk that up and put it on the back burner, because rerunning and extracting the data could take, a couple of weeks. And finally, this C++ code, this n-tuplizer, this thing that does the private skim, everybody writes one. And about 80% of the variables you extract are exactly the same from one analysis group to another. So this is wasted effort by the collaborations. We could be doing more physics rather than more data. Next slide, please. So the idea is to try to replace this skim by using a service which can effectively query, and it will pull quickly just the data branches that you need. And we do this by sticking this service at a location which is very close to the centrally managed data set. And we don't do very much processing during this query. So we very quickly spin through the data and extract the data, and then we do all the real processing. This is called, we call this service X. Let's go to slide 19. And you can think of it as feeding the awkward or jagged arrays that Jim was just talking about. It's one place for it in the ecosystem, is that it would feed that data, and then the awkward arrays would feed things like the statistical model, some of the things that Matthew was talking about in those outer rims of that ripple pool, that figure that he showed earlier. So I want to go through very quickly the steps that this does, and then I want to just talk about some observations that occurred to me as a physicist as opposed to a software engineer as I worked with some others to develop this. So first, the user queries the system. This is a REST interface, a web API. So we're using a well-understood web standard. Maybe it's not so well understood by us physicists in general, but it's certainly well understood by the open source and business and open source and business community. In this query, you specify your original data, what data you want to extract, some filtering, so maybe not all of the collisions, for example, but some subset of the collisions, and then perhaps some derived quantities. You could do a reconstructed mass. You could do, pretty much any calculation you can do with math. The point here is that you only want back the data that you're going to need, and you leave all the extra data back in this high bandwidth data center. Further, since it's a REST query, everything about the query goes into that, all that information goes into that query. Thanks, Matthew. You were actually almost exactly right for the next slide there. Okay, so the second thing is the now internal in the service is we build the code that will actually extract from the file. The type of code that gets built is arbitrary. Wow. Sorry, I apparently was not awake enough when I typed Python there. So Python, C++ really depends on what the code is. It's flexible and it depends on your data set. And then the other thing you need to do, of course, is have the source files that you're going to run over. Petabytes or hundreds of gigabytes corresponds to often thousands of files. So this is a preparatory step. It's extremely quick, and it's getting ready for the next step, which is the transforming step, which is slide 3. It's the next slide, which is step 3. And here the data is transformed to the requested output data. Up to some preset limit, a number of processes are spun up for every file. So in one of the tests I'll just reference briefly in a minute, we had 1,000 of these transformers all running at once. And as long as the bandwidth is there, you can run 1,000 whatever files in parallel. And the extracted data comes out in a columnar format, which is exactly what Jim was talking about, jagged but columnar format, which makes it so convenient to access not only in the Python ecosystem, but in a number of legacy tools as well. Next step, please. Next slide, please. Finally, the results are stored in an internal database. We use what looks like basically an S3 object store, which is the AWS protocol. And the beauty of this is it's now cached, and it can be requeried, and you don't have to rerun. You just go fetch from the database. And since everything was completely specified in that original web query, you can hash that. And so the system could notice, hey, we've already run this. We don't need to run it again, and immediately just return the results rather than have to rerun. This data can then be streamed to a DAS farm for more complicated or sophisticated downstream servicing, for example. Nominally, these are taking, a petabyte of data and turning into gigabytes. I should say gigabytes plural of data, depending on what you're doing. Slide 23, please. Okay, so this is the last slide that I wanted to talk about. Now I've given you some context. I just wanted to make some points. We wrote very little code of our own. And this really surprised me because as a physicist, I always start by, how would I solve this problem? Well, let me write a little dummy piece of code. And that dummy piece of code quickly expands to be a production system, which grows organically and is untested and is super horrible. As a friend of mine that I worked with told me, who came from industry repeatedly, I would have been fired if I wrote code like that in industry. Maybe a way to take a step back and think about this is we should maybe stop thinking about how to solve a particular problem and ask first if somebody else has solved it. Now, as a physicist, I don't always know the right form where to ask that, but there are people around, for example, some of the people here who very much know that answer. The other thing that I learned is I really need to stop thinking about single computer, single process solutions. In particle physics, our data is certainly big enough. We need to think outside this, and this is my comfort zone. Usually, my approach is get it running on one computer and then figure out how to scale it up. Many folks out in industry take the opposite approach, like, well, we know it's going to be big, so why do we even think about a single computer solution first? Let's just start from multiple computers from the get-go, and maybe we can squeeze it to run on one computer to do development work. This, in the end, becomes not about the code that I can write as a physicist or a software engineer or whatever. It's about the ecosystem that I live in, because I can take advantage and steal everything from this ecosystem, and thus make much more progress and instead concentrate my time on things that are important for my specific domain, like particle physics. The most efficient by far way that, the way we made progress here was by collaborating with somebody who knew the ecosystem and the tools. I mean, we stole Kubernetes, we stole RabbitMQ, which is a message broker, SQL, Postgres, MinIO for the S3, and it was a matter of putting these things together and then building in Python, because Python's ecosystem means it talks to all of this stuff with just their libraries that exist that allow you to use it. And we just had to write a couple of small little apps which glued all these things together and sent messages in the right order to the right components, for example. And it turns out these are hundreds of lines. And if we tried to write something like this with auto scaling and all this other stuff, would have been, well, I don't want to even talk about it. So as an example, one of the tests we did was a 10 terabyte data sample. And we pulled out 100 columns of data, which was 30% of the file. So this is quite a bit, a large percentage of the file. And it took less than 30 minutes running over the network, which, for particle physics is super good. Okay, Matthew, I think that's it. It might be back to you.
Yeah, okay. So, so thanks, Gordon. Thanks, Jim. So kind of to wrap things up with some conclusions. Hopefully we've shown you that through a confluence of scientific tools and developers, engineers, and scientists, we've kind of started to reach a full feature-complete Peickert-HEP in the last 5 years, and this really has kind of been a true community story effort. So what you're seeing here is a slide stolen from a presentation that Eduardo Rodriguez, who is one of kind of the founding members and visionaries of the Peickert-HEP project, he was showing at a workshop to the High Energy Physics Software Foundation back in 2017. So this is something that has kind of been an organic community movement, but when you have big projects like IRIS-HEP that are also providing the support, you can and also supporting the personnel, you can go from having an ambitious idea to actually having a reality in half a decade for our field is pretty fast. So that's pretty amazing unto itself. And then on slide 25, we have this growing Pi-HEP ecosystem. We're really trying to make sure that it's actually enabling analysts in higher geophysics to explore and reduce the time to insight. And I think that Gordon's example here on slide 23 is kind of a beautiful example of that, because as you mentioned beforehand, this is something that would literally take weeks. And now this is something that you could essentially say this is a long coffee break or something, right? So this is truly, for our field, pretty revolutionary, and we're really excited to try and make sure that this keeps on moving. So with that, I think that's all that we actually have in terms of formal remarks. So thanks to everyone so much for your time and attention, and I'll turn it back over to the organizers to see if there is any questions.
So I want to take just a couple of moments, a couple of questions or comments from our host and our guest panelists to reflect on what we saw there, or from the audience. If you're in the audience, feel free to put your questions in that Q&A widget or in the chat. First, I want to give an opportunity to our host panelists if they have any follow-up questions, because I have one. And it's touching upon something that we heard or we saw in that last slide, the idea that don't go off and build it yourself, see if it's already been built. Well, it occurs to me that some scientist is going to say, you know what, I don't want to do all the work to build something myself. I'm going to go see if somebody else has done the work. And they're going to go and find some great looking package that they can find online. They're going to put in some effort to figure out, oh, is this useful for my work? They're going to discover, oh, it doesn't solve this one corner case of what I want to do, and they're going to go have to write something themselves because what they thought would solve their problem doesn't quite solve their problem. And they'll think to themselves, well, you know what, I should have just written for myself from the very beginning. I shouldn't have even gone down this process. How do you give somebody some guidance for where that cutoff point is between actually go and try to engage somebody's external code versus, you know what, maybe you're not going to really get anything out of that, and maybe your intuition to just write it yourself is fine. Andy, I see you went off mute.
I was going to ask a question, but you asked yours, so.
Okay, we'll come to your question in a moment.
Yeah.
So I'll start here, but I think Matthew and Jim, as leaders of open source projects, can also will have some very interesting things to say here. But one thing I've noticed working with my students is once they thoroughly get into this idea of I'm not writing it myself, I'm working with others, I'm working with packages and libraries. But the key is to find a package which is under active maintenance. And if it's missing an edge case, that's a pull request. And I have to say, coming to this community, the open source community, I'm relatively new. I don't think it's been more than 4 or 5 years. The willingness of people to accept well-tested and code that conforms to their specific formatting, et cetera, but the willingness is high. People are happy to work together. Both Matthew and Jim should also chime in here because they're both leading rather large projects, which I think have both taken advantage of this network effect.
Okay. Actually, you hit what I was going to say is that it's hard to. I'm getting confused with overestimate and underestimate. The people who are developing large packages, famous packages, JAX at Google or NumPy, the king of them all, they're very approachable. You realize that it's just like walking down the hall and talking to someone when you open a discussion with them about, adding some feature or something like that. So you were asking when is the cutoff. It is important to be able to get a sense of what is a small change on an existing system, something that it makes sense that it would be within their envelope, and just talking with them can help you figure out what their envelope is. To know whether there's a small addition to it, or if what you're doing is like qualitatively different. It's really a different basis in the vector space that should be around. But again, it all comes from talking to them. It's amazing how approachable developers of very famous software packages are.
I'll just echo everything Jim said, and then to give kind of a specific example also of where maybe the contribution that you're thinking of or the thing that you want really isn't in scope. It's maybe too broad or outside of scope. I think a fantastic example of both community and way of supporting this is Matplotlib, one of the friendliest communities around. And then I think something they do exceptionally well is they have their third-party kind of contributions where they don't want to have everything be inside of Matplotlib because you have to maintain that. PRs are like puppies, as we've heard Brett Cannon and other people talk about. But they very much welcome and encourage that their community members build upon Matplotlib, and they want to highlight that work too with their third-party community pages.
Fantastic. Why don't we move on? Andy, you had a question?
Yeah, I was just sort of curious from like a naive standpoint, and maybe some of our audience that aren't in high energy physics might be wondering too. In terms of SciPy's really extensive histogram, seems to me to meet my needs. When would I maybe start to reach for the HEP community's histogram packages? And do I have to be a physicist in HEP to understand them?
You don't, and they're not complex or anything like that. Here's a difference in basis. Like, is it different enough? We can scan over all of the histogramming capabilities, like numpy.histogram, matplotlib.hist. Pretty much all of these. Any package that displays or comes close to displaying something will have some kind of histogramming function. What we need that's qualitatively different is a histogramming object. Something that maintains state, you can pass around. And the reason that we need that is because all of our processing is from the beginning out of core. We are almost always making histograms on data that will not fit in the memory of any computer. And so we need to make these long-lived histogramming objects that, maybe you've got 100 jobs running, and each one of them is creating their own histogram objects. They send those objects back. Those objects get added, to make the full histogram. And that's it. It's not a complex difference, but that's just not what MPL.hist does.
To add on to that, I know that NSLS2 is a new facility, but we're already looking at upgrades. And I know APS is going through upgrades. A lot of these DOE facilities want new things. And at the top of the wish list for many scientists is new detectors. And we're seeing a change from the common detector being a traditional framing detector to being a more event-based detector. And who was doing event-based analysis before it was cool? Our friends in higher energy physics. So I anticipate increased interest in histogramming, perhaps an awkward array, over the coming 5 to 10 out of the DOE user facilities.
Fantastic. Now let's take one or two more questions. I noticed we had a question from somebody in our audience in the chat. How do you know that existing code is correct or bug-free? I think this is part of the challenge. Maybe don't do it yourself, but if you do it yourself, you only have yourself to blame, whereas if you use somebody else's code, anything goes.
Test. I working with my students, the very first thing is what you need to do a unit test or some sort of test in the library that you're looking at. So I encourage people to go look at those tests. And the other thing is that when for me, when I incorporate somebody else's library, I need to test that library interface and make sure that I'm passing the arguments or whatever to the library in the correct way from my library that's a client. So what test case do I use? The one I'm probably, using the library for. And so I effectively am testing, it's a little bit more of an integration test in that particular case, but I effectively am testing that because that is so true, is looking for that sort of thing.
Yeah, I would totally echo that. I mean, I think we can also all agree that learning how to write good tests is a skill that needs a lot of fostering and development as well. But I would also say that, no code is going to be 100% bug free, even if you have that nice 100% code badge on your repo. Probably don't have, 100% of all integration tests that you could ever think of covered there as well. So not to, give them work, but if you can lean on your community to make them and make sure that they feel confident that they can report bugs or report things that they think are bugs, and they're not going to get, nope, won't fix, close issue, and, make them feel like they're being pushed away. That's a really powerful thing, to have a community that's more than happy to, hold you accountable in some sense, but also to help let you know when you have missed things. That's pretty helpful.
Any final comments? Otherwise, I want to direct us to one last question and then we'll adjourn.
I would just say I take more of a practical approach. I'll see if the library has a forward simulation and then back simulate, or find data that is already analyzed, like even in a paper where they have the parameters, and use ways to extract the data from the paper to then see if I can't reproduce the result.
And for our last question, we have a fantastic question that came to us via the Q&A widget. Let's see if we can, within some tight time bounds, answer it. One of our attendees asks that in slide 23, you mentioned to stop thinking about single computer code as if it's going to be scaled up. But wouldn't this be the process anyway? As in, you'd first write the code, make sure it works, and then scale it up? Is the suggestion that you would think about this in the multi-computer sense, in the scaled up version first?
Okay. Yeah, I understand. I understand where I guess it's Brian is coming from here. It's indeed true. The point is that you, for example, in the Surface X case that we were talking about there, we never wrote a system which ran inside a single process. That was not done. We started by writing that distributed system from the get-go. So when for example, each of those transformers is just a single process. So we didn't belly up to this problem by just trying to write the transformer and then writing some code around it, which we would just run. Instead, we started thinking about how are we going to get the files to that transformer, and then get the transformer code linked with the message queue, which was doing the file handoff. And the reason that I think this was a lot better was, having gone at this in the other direction, the code that runs the single process just stays there forever. And it's in a one branch of an if statement that does not get used for 3 years. And then you come back to it and it's old and crufty and probably doesn't actually work anymore because it's not been tested in ever so long. So that's what I meant. For more modern things, you can see this with, and now I'm going completely off track here, but you can see this with GPU development. People are not thinking about anymore how to write some of the computational algorithms by writing it on a single processor. They're just saying, I need to build an algorithm which will be most efficient on a GPU, and they're starting from that, and they're taking a completely different look at the algorithm. And so all of a sudden, new possibilities are arising that don't when you come from the single process, the single thread point of view. And this is what I'm trying to encourage in those statements. We're in a world now where we are at some level getting to the point where we are trading for disk space, we're trading CPU for time, for our time, or the researchers' time. And the result is that in order to truly take advantage of this, we've got to scale up to many cores. We can't sit there on a single core anymore. And so, I'm now over 55. When I said I am your guy for Fortran, I was serious. That's where I started. And as you might imagine, it was a single process. So all my thinking is sort of built around that, because that's what I learned as a grad student. And I think that's now become a real liability for me. I have got to break out of it and think of it think of things multi-core first, and then, okay, maybe sometimes the problem does make sense to just do it single core. It's not that every problem is multi-core, right? But we should be thinking about it from that point of view, because this is what we have available to us now, and this is how we scale our problems. I hope that was helpful, Brian.
Fantastic discussion. Why don't we leave it at that? And I see that we're at the time that we had allotted for this call. Why don't we do the following? Let's adjourn at this point, and we'll resume again next month on July 27th at the same time slot, when we'll be hearing from one of our colleagues from Los Alamos National Lab, Jan Jansen, who will be talking about PyIron, an integrated development environment for computational materials science. I know I'm excited to hear more about this, and I hope you are too. Thank you to all of our guests and host panelists for being part of such a lively discussion this month. But with that said, we'll see you all next month for the next Python Exchange. Thanks, everybody.